Welcome to Maths with Bob. Today we're looking at HCFs and LCMs, sometimes called highest common factors and the lowest common multiples. Now the first thing we need to work out is, what is a factor? Okay. A factor obviously is a number that goes into another number. For instance, say let's have a look at 12. Okay, some of its factors are what? 1 times 12. Okay, so 12 and 1 are factors. How about 2 and 6? Okay, so 2 and 6 are in fact factors. How about 3 and 4? Okay, 3 and 4 are in fact factors of 12, right, the number 12. Okay, so 12 here, okay, its factors would be, let's have a look, 1, let's list them out, 1, 2, 3, 4, 6 and 12 itself. So that would be a list of the factors of 12. Okay, so let's have a look at the multiples. Okay, some people actually say, I heard this term, gazintas. And I thought to myself, gazintas. But it's short for goes into. So a factor is something that goes into the number itself, okay, as opposed to a multiple, which is actually obviously a multiple of the number and hence much bigger than the number. And factors are obviously smaller or equal to the number. Okay. And a lot of this relies on you knowing what a prime number is, and we're going to be looking at that in a minute. Okay, so let's have a quick, okay. What is a multiple? Okay, let's have a look at 12 again. Well, the multiples of 12 are obviously, hopefully we all know our 12 times table. Okay, 12, 24, 36, 48, etc. Okay, these are all multiples of 12. Okay, so the first multiple of 12 is 12 itself. Okay, the second multiple is 24, and the third multiple 36, etc. So multiples are obviously starting at the number and just basically multiplying the original number by like 1, 2, 3, 4, etc. to get what's called the multiples of the original number. Okay, so in fact, let's do this one. Okay, what are the multiples of 12? Okay, they would, as obviously just above there, 12, 24, 36, 48, etc. These would be the multiples of 12. Okay, so now we hopefully know what a factor and a multiple is. We're now going to try and find out what's called the highest common factor and the lowest common multiple of two numbers. So it actually can be more than 2, it can be 3 or 4, but we're going to start off with 2. Okay, well it also is very useful to know what a prime number is, and hopefully we all do know what a prime number is. Okay, prime is only divisible by 1 in itself. Looks like it's missing there. Okay, by 1 in itself. Okay, so it's something which is not prime is called composite. Sometimes you get the primes close together, differed by a couple, like 7 and 11 and 3 and 5. Sometimes called twin primes, and you can basically look at the the factors. So, but this all relies on something called the unique prime factorization of numbers. So each number has what's called a unique prime factorization, and this allows us really to help work out what the factor trees are for the numbers, and then work out what the highest common factor and the lowest common multiple is. Okay, so what are some prime numbers? That's okay. Well, the first prime number is 2. Okay, 3. Okay, is 4 a prime number? Hopefully we know it's not. 5. Okay, 7, 11, 13. Okay, and as we get bigger and bigger, actually the primes start getting more and more sparse, if you like, and a lot of cryptography relies on very large primes, which are few and far between, I guess you could say. Anyway, so the idea is that we need to work out what's called the prime factorizations of things to find what's called the factor trees. This is going to help us find the HCFs and LCMs, but we also need to know something about what's called divisibility. So we need to actually, before we can actually find, I guess, or do a factor tree, we need to look at what's called the divisibility tests. Now, I've just written them down. I'll just show you. Okay, here are the divisibility tests. Most of us do know, I think, obviously something that's even, ends in a 2, okay, well, divisible by 2, I mean, ends in 2, 4, 6, 8, or 0, okay, is an even number, it must be divisible by 2. Okay, have a quick look at these. 3, sum of the digits is divisible by 3. 4, the last two digits, or the number formed by the last two digits is divisible by 4. 5 is a pretty easy one to pick, as is 10. 6 has to be divisible by 2 and 3. Now, 7 is a bit of a tricky one. You actually have to double the last digit and then look at the remaining digits and take that number off it. And then if that is divisible by 7, then the number is divisible by 7. 8, the number formed by the last 3 digits, you can see here, is divisible by 8. 9, okay, the sum of the digits is divisible by 9. Obviously 10, again, easy one, we said before. Now, 11 is a bit of a tricky one. The sum of the odd digits minus the sum of the even digits is 0 or divisible by 11. Now, I guess it depends on what end do you start counting the digits from. Well, you start counting them from the units, okay. So the first, you can see here, 6, 2, 8, 1. The 1 is the first, so it's an odd, and then the next odd one is actually 2. 8 is even, and 6 is even, and you can see here, I just did a quick example. So 6, 2, 8, 1 is in fact divisible by 11. Now, if it's 12, obviously it has to be divisible by 3 and 4, so you have to apply the divisibility test for 3 and 4. Okay, so we'll now have a look at some factor trees. And well, let's actually start looking at some factor trees. Okay, let's just do one. Okay, 60. So we write down the 60. We then do some branches off the 60, if you like, and start listing its factors. Well, we know it's 6 and 10. Okay, we know 6 and 10. We also know 6 is actually 2 and 3, and 10 is actually 2 and 5. Okay, now it doesn't matter how we do this. We could have actually gone, let's have a look, let's try another way. Okay, 60, okay, let's have a look. Let's have a look, 10, it's 12, 5 12s, okay, okay, 12 and 5, okay, 2 and 6, and 2 and 3. Now, if you look at the leaves, okay, let's have a look at the leaves, okay, so the leaves are, in this case, you can see here, around here, these are the leaves down there, 2, 3, 2 and 5. And you can see the leaves on this one are a bit, well, they go sort of they go around here, over there, and all the way here. So the leaves are sort of a bit more sort of strangely spread here. But what we do is when we actually write the prime factorization of each number, is we just actually list out these prime factors, or if you like, the leaves at the end of the branches. So let's have a look. So 60 is equal to what? 2 times 3 times 2 times 5, and hopefully, obviously, it's the same here. 2 times 2 times 3 times 5. Now, we normally also start to use our index laws, and so we would write, if you like, you can see here 2 times 2 is 4, but we normally write that as a power of the prime. So we go, okay, 60 would equal 2 squared times 3 times 5. We call this the prime factorization of the number. Okay, see here we had to go over that 2 there, but 60 is 2 squared times 3 times 5. Okay. Okay, well, let's look at another number, say 105. Okay, well, hopefully we know that that's divisible by 5 because it ends in a 5. So what is it? 5 times 21. 21 is 3 times 7. Okay, so we'll just say that 105 is actually 3 times 5 times 7. There's no repeated prime there, just 3 times 5 times 7. Okay, so that's not too, that was a reasonably easy one. Okay, so when the numbers get bigger, obviously the trees get bigger as well. Okay, well, let's have a quick look. We're now going to find the HCF of these two numbers, 60 and 105. Now, it's always a good idea to rewrite their actual prime factorizations. Now, you might remember 60 was equal to 2 squared times 3 times 5, and 105 was just 3 times 5 times 7. Now, how we find the HCF is we look at the common primes. Now, not all the primes, the common ones, they have to have them in common. So which ones would they have in common? Do they have a 7 in common? No, they don't, obviously, we can see here. Do they have a 3 in common? Yes, there's another one down here. Okay, 3 in common. How about a 5? Yes, one here, and obviously one here. Okay, so we have a 3 and a 5. Do we have a 2? No, obviously not. Okay, so what we do is we just write down common primes to start with. Okay, we look at, so it's 3 and 5. And then we look at the powers. Now we have to use the lowest powers of the common prime. So I'll just write this here. It's the lowest powers of the common primes. And we have them here. Because 3 and 5 are both to the power 1. Our HCF, well, yes, is in fact 15. So this is the HCF of those two numbers. Okay, let's actually look at what's called the LCM now. How does that differ from the HCF? Okay, well, how do we find the LCM? This is the lowest common multiple. Okay, it's the lowest common multiple between them. Now, the highest common factor is actually, remember, the highest factor that goes into both of them, which was, we remember, was 15. So let's have a look. How do we do this one? This one is slightly different. We have to write down all the primes. Now, this is the difference, okay, not the common ones. This is all the primes. So it's 2 times 3 times 5 times 7. Okay, so it has to be all the primes, okay? So, and then, just fix up that 5, didn't look too good. Okay, so here we are. So 2, 3, 5, and 7, yes, they are all the primes. Now, the only thing here is we have to use the highest powers of all the primes as well. Now, most of the primes you can see there are of power 1, but the 2 is of degree, or power 2, if you like. So we need to actually basically use the highest powers, not the lowest, of the common, which is the HCF, okay? The LCM is all the primes multiplied together and using the highest powers that are occurring in the individual numbers. Okay, so now it's okay. So first, let's write that down. So it's all the primes, okay, all the primes in both numbers, okay, and it's the highest powers. Okay, now, so we now need to work out this, okay, 7 6 of 400, looks like about 420. Okay, all right, let's actually, so that 420 would be in fact what's called the lowest common multiple of both the numbers 60 and 105. So 420 is called the LCM of, so sometimes some people write it like this, LCM 60, 105 is equal to 420. Okay, all right. Okay, so let's do a harder example now. Okay, we're having a look at a harder example. We're going to find the HCF and LCM of these two numbers, 1750 and 945. Now, let's actually go through how we do this. Okay, so the first thing you do the factor trees. Okay, so you say, okay, that's 1750. Now, most of us can see that's obviously divisible by 10, 175. We know 10 is 2 times 5. And we know that 5 will go into this as well. It ends in 5. So 5, 3 5s are 15, and 25. Okay, so it should be 5 and 7. Okay, so we could say that, what's the prime factorization of 1750? Let's write it. What's it? 5 is cubed and 2, so it's actually 2 times 5 cubed times 7. Okay. Let's have a look at the other one, 945. Now, 945, okay? Well, we see it ends in 5, so we can straight away go, okay, 5, and then we have to go divide that into, I think it's 189. Now, we get 189, and we think, ooh, what number goes in 189? Well, if you look at your divisibility tables, if I add the digits, and you can see here they will add to 18, and that is divisible by 9. So we know that, 9 will go into that, 9 will go into that. In fact, what does it go? 21 times, and obviously 21 is 3 times 7, but remember 9, we have to keep on going 3 times 3. So what is the, prime factorization, if you like, of 945? Well, you can see here it's 3 cubed times 5 times 7. Okay, now all we have to do is to find the HCFs and LCMs is, in fact, to use the ideas of common primes, lowest powers, or all primes, highest powers. So let's actually do that now. Well, okay, the HCF is pretty easy. We can see which primes are common. Let's have a look. Which ones would be common? Well, 257, 357, okay, 5 and 7, yeah, okay, 5 and 7. Now, okay, 5 is to power 3 in 1750 and to power 1, so it's the lowest one, so it's actually just 5 times 7. So you can see here, that's easy, it's 35. So 35 is the highest common factor, or if you like, the highest number that goes into 1750 and 945. Now let's actually now do the LCM. Okay, so we want the LCM of, say, 1750 and 945. How would we do this? Well, first thing is you have to write down all the primes, okay? 2, 3, 5, and 7. So 2 times 3 times 5 times 7. Now we have to use the highest powers of these now. 2 is to the power 1, that's okay. 3 is to the power 3. 5 is to the power 3, and 7 is to the power 1. Okay, so now we're going to generate a fairly big number. Okay, I think it's 47,250, okay? 47,250. Now, okay, this is the number, okay, the lowest common multiple of those two numbers, 1750 and 945. Okay, now we can extend this to 3 numbers, 4 numbers. We can even extend it into algebra and all sorts of things. But it's a fairly powerful idea, the idea of using a factor tree and the unique prime factorizations of numbers together. Well, thank you for watching, and bye for now.